All kinds of big. That's my title. I tried to come up with a cute little title. I don't know if that does it or not. Anyway, here's the goal for the talk. We're going to describe every possible notion of bigness for subsets in space. By the way, I prepared this talk with the expectation that a lot of the non-math sort of summer science research students would be here. So welcome, Craig. We have a few. Yeah, I guess I don't know all of you, so maybe some of you are of that nature. I hope that this is understandable by everybody. I'm going to be a little bit vague about the mathematical details from time to time, but if you want clarification, feel free to ask. And I'm going to try to explain everything anyway. Every possible type of notion of bigness. So this is Hadwiger's theorem, and I'm going to define what I mean by these various things. But basically, if V is a measure of bigness in Rn, then V must have the form, etc. All right, this is the theorem that we're going to get to eventually. But the theorem is a complete description of all possible measures of bigness for sets in Rn. All right, and I'm going to say what measure of bigness means. Oh, here's a little, just to keep you informed, little graph here. This is the density of jokes per slide in this talk, so be prepared. All right, I kind of crammed them all together. I hope you don't mind. No, this isn't it. This right now, this is not a joke. This is very serious. Yeah, this was actually, I kind of faked it on this one. This is really sort of a self-referential slide. I would have had to do a lot of thinking, which I didn't do. You note the bottom axis is not labeled because I didn't want to try to predict exactly where I was going to put this. Anyway. Okay, let's talk about what do I mean every possible type of measure of bigness for subsets in space. There's a lot of things that need to be defined there. So measure of bigness for subsets means specifically a function which is going to assign a real number, which we're going to think of as the size of a subset in Rn. Such a function should obey these three properties. All right. First of all, it should be a rigid motion invariant. If you do a rotation or a translation in Rn, that should not change the size. I hope that seems reasonable. It should also be continuous in the sense that if you change the set that you're measuring a little bit, then that should change the size only a little bit. All right. And those are the two sort of simple properties. There's one other property that I'm going to say any kind of notion of size or bigness should satisfy this last property, which is called the valuation property. The empty set, that's this thing. The size of the empty set is going to be 0. And this property should be true. The size of a union should be equal to the size of the first set plus the size of the second set minus the size of the intersection. And if you think geometrically about that, that should make complete sense. This is sometimes called the inclusion and exclusion rule. In combinatorics, it's usually called this. In analysis or in algebra, such a thing is usually called a valuation. All right, so what this means in a picture here, if this is the set I'm trying to measure, you break it down into two sets, A and B. Say A is the red one, B is the blue one. And then they have some intersection, right? And if your function measures bigness in some sense, it should satisfy this property that the size, the bigness of the whole thing on the left is equal to the sum of the two sizes of those two parts minus the size of the intersection. All right? So this is a fairly, I hope you all agree, if you're talking about anything which measures in any sense the size or how big something is, it should satisfy this property. All right? And this is basically the only property that we're going to assume these things satisfy. So there are three, really. There's the invariance under motions, continuity, and this property. All right? Anything which satisfies those three properties, that's what I'm talking about when I say a measure of the bigness. All right? So this talk is about all possible kinds of measuring the bigness of things. All right? I'm sure.
Positive?
No. It should map into real numbers.
You can have negative bigness.
I guess so, yeah. Yeah. So your mind should be going wild a little bit. You could imagine, I mean, there should be lots of even like insane or crazy functions which still satisfy these properties because they're not very specific properties. Okay, so just technically by measure of bigness, I mean continuous invariant valuation. Invariant is when I say invariant, I mean invariant under rigid motions of Rn. All right, which is defined on subsets of Rn. Okay. These are some big words, but I hope you agree. This is what I just said. This is the bare minimum of what you think bigness should mean in Rn. All right. So the area is one such function. The picture that I just showed you was really about the area. But, like I said, there are many other functions. Here's a little technical interlude for the mathematicians. Actually, we have to be a little careful about what subsets you're allowed to be measuring the bigness of. You may have heard of, there's some crazy kinds of subsets which will totally mess up everything. If you allow any subset, there's something called the Banach-Tarski paradox, which is a paradoxes in mathematics are true facts that just seem crazy. But it says that it's actually possible to have a set with volume 1. You can chop it up into really weird subsets, move them around, and reassemble them so that the total volume is 2. This is actually possible. It's called the Banach-Tarski paradox. It involves using non-measurable sets in Rn, which are really crazy. Anyway, the moral is I don't want to allow you to do things like that, because then basically nothing will satisfy the valuation property if you're allowed to do this kind of a thing. So the volume and the area, things which we typically think of as bigness, for these sort of pathological sets don't work the way we expect them to. So we're going to restrict the kinds of sets we're considering. So the sets which we consider are always going to be closed, topologically closed sets, and what's called polyconvex. Hopefully you've heard of a convex set. A set is convex. It means the straight line connecting any 2 points in this set. If you draw the straight line, that straight line is also in the set. I don't want to get too much into this, so I don't have pictures, but it's a pretty simple notion. And a polyconvex set means any finite union of convex sets. And so if you think about it, pretty much any kind of ordinary type shape you can think of is probably polyconvex, or at least very close to a polyconvex set. Any kind of polygonal type shape is polyconvex. This is what I just said. Any ordinary shape you can think of is arbitrarily close to a polyconvex set. So this, by requiring everything to be polyconvex, we are going to rule out just sort of ridiculous, insane sets. All right. And also the continuity assumption, technically speaking, we are going to assume that the thing is continuous on convex sets. That is to say, if you have a convex set and you change it slightly into another convex set, then the thing is continuous when you do that. All right. Anyway, I'm not going to get into those kind of details very much. So some examples of continuous invariant valuations, which is what we're talking about. In R2, we have the area, right? The area of the thing on the left is equal to the area of those two things minus the area of the intersection. I hope this is what I intended for you to be thinking about when I showed you this shape before. Actually, though, the same shape, there's another valuation that you can see on this shape. The perimeter also has the same property. If you take the total perimeter of this thing over here, where I mean you take the arc on the outside as well as the two arcs on the inside and add together that total perimeter, it is actually, take a minute to think about this, it's true, it is actually equal to this perimeter plus this perimeter minus this perimeter. All right? You get some sort of extra perimeter when you make this cut here, but that gets subtracted away when you take away the intersection, and everything works out. All right? So the area and also the perimeter are continuous invariant valuations. So you could say something is big with respect to the area, or you could say something's big with respect to bigness of perimeter, right? Okay, in R3, we could do similar kinds of things. We have the surface area that you could measure the surface area of that thing. Actually, if those are unit spheres connected by unit intervals, then the surface area would be 12 pi. I had to look up the surface area of a sphere. It's 4 pi r squared, right? There's 3 of them, so surface area. There's also the perimeter. I put it in quotes here. What I mean by perimeter in three-dimensional space is the sort of sum of all the kind of one-dimensional components of these things. In this case, it would be 3. There are 3 line segments. Those spherical portions don't have any perimeter because there's no one-dimensional boundary to them. All right? 3. And the volume? Oh, I was going to say, is there any other way that you could measure size of sets in R3? I didn't set that up properly. The answer is the volume, right? So you can do the volume in this case also. And that also satisfies the valuation property, all right? And the volume in this case is 4 pi. What's the relationship between these numbers? It is a complete coincidence that the perimeter times the volume is equal to the surface area. That's a meaningless fact, all right? So in R2, there's the perimeter and the area. In R3, there's the perimeter, the area, and the volume. All right, yeah?
What about the measure of curvature? I mean, last week we were talking about polynomials.
Uh-huh.
Would that be a measure of bigness?
I don't know. I mean, you have to think about, does it satisfy that valuation property? And I'm not sure.
It satisfies two of them. The rigid motion thing, it sort of depends on, like if you're talking about surfaces in R3, then they're not polyconvex, but then if you're talking about subsets of R2, then there is no holonomial. So it's pretty close, but it doesn't quite fit this. But we did, the valuation property was essentially something we talked about, and where you added up the pieces. And the continuity we kind of talked about in a backhanded way.
Mm-hmm. Yeah, there's actually something about curvature. I'm gonna mention something vaguely about curvature later on. So, good question. Okay, we got the volume, right? Which is like the three-dimensional size. The surface area is kind of like the size of the two-dimensional boundary or the two-dimensional edge of the thing. The perimeter, I'm going to call the size of the one-dimensional edge, if any. These are called the intrinsic volumes in dimensions 3, 2, and 1. All right? And in higher dimensional spaces, in Rn with n bigger than 3, there are higher dimensional intrinsic volumes. There's the dimension 4 intrinsic volume, and so on. All right? Oh, a little update. Remember that? This doesn't count either. That's not a joke. So the intrinsic volumes in each dimension are continuous invariant valuations. So they are sort of bigness functions, the things we're looking for. The big question is, are there any others? The answer is, yes, there are. And that's what we're going to talk about. So our goal is to describe all possible continuous invariant valuations. There's the intrinsic volumes, and then there's some more. What are they? That's what I mean by all kinds of big, right? So, what kinds of big are there? Big? The film by Tom Hanks? Anyone know who that is?
Mr. Big.
Yeah, Mr. Big from Sex and the City. Mr. Big, the 80s hair band? Remember them? Maybe not. I do.
Does anybody remember?
You remember there was sort of a one-hit wonder. Anyone name that tune?
I can't remember.
I'm not gonna. I'm the one who wants to be with you. Remember that?
Yeah, that's right.
Sort of a power ballad. Yeah, stupid song. Anyone know this guy? This is Mr. Big, the James Bond villain. And of course, anyone who knows me, I got to throw this guy in. Biggie Smalls, you know, the notorious B.I.G. Yeah. Rapper, deceased. He lives on in our. It's all over now. You can leave. Still food here. Okay. Besides the intrinsic volumes, are there any other continuous invariant valuations? That's what I want to talk about. Here's a stupid answer. How about 2 times the area? I said the area is a continuous invariant valuation. 2 times the area is also not the same as the area. You might say, oh, that's the same. It's not really. Not exactly the same as the area, right? So 2 times the area is also a continuous invariant valuation. In fact, any continuous invariant valuation can be multiplied by a constant, and the result still is a continuous invariant valuation. It just that property about the intersections, it still holds if you multiply everything through by a constant. All right? Here's a really stupid answer. 0. That is, what I mean is, you just say everything has size 0. All right? That still is continuous, still invariant, and it satisfies that valuation property because everything, if you just say everything has size 0, then it's still true that thing adds up in the proper way. All right? So these are kind of stupid variations on the valuations we've already got. Also, you could do the perimeter plus the area. If you add 2 valuations together like that, any sum of 2 continuous invariant valuations is another continuous invariant valuation. All right? These are all kind of stupid, maybe not so stupid, but they're variations on the ones we've already got. Anyone want to fill in the blank here? There's a blank at the end. The set of continuous invariant valuations is a... I just said you can multiply any continuous invariant valuation by a constant, and you get another one. You can also add any 2 together, and you'll get another one. Also, like, the 0 function is one of these things. What is it? Yeah, it's not the word I was looking for, but yeah, it's a vector space, right? You can add together these things, and you can also multiply them by a constant, dare I say, scalar, right? It's a vector space. So when I ask you how many continuous invariant valuations are there, the answer is infinitely many because you can scale them up and down. Vector space, I filled in the blank, all right? Really what we should be looking for is, there's infinitely many, but we can still try to find a basis for this vector space, which would mean sort of, okay, fine, There's infinitely many, but they're all sort of variations of each other, right? What are kind of the ones what they're all based on, right? That's what I want to get at. So the idea I want to get to, other than the intrinsic volumes, are there any other really different ones that are not just obtained by adding together the intrinsic volumes and multiplying by scalars? The answer is yes. If the answer was no, then I wouldn't have much more to say, although that would be an interesting fact by itself. The answer is yes, there are other continuous invariant valuations. So here's a definition of another one. I'm going to define this valuation chi like this. If A is a convex set, then chi of A is equal to 1 for any convex set. And then if you have something which is not a convex set, you define this valuation by breaking it up into convex sets and then using the valuation property. All right. So otherwise,
What's a convex set?
convex means 2 points. The line between them is in the set. It's contained in the whole set. I'm going to draw a picture in a moment. So if it's convex, you just say that it has size 1. Otherwise, you compute the size in terms of smaller convex sets by adding and subtracting intersections. All right. So for this set, this valuation has value 1 because that's convex. Any 2 points in the set, the line between them is still part of the set. But this is not convex now because it's got that hole in the middle. So we break it up like so. Break it up into 4 convex sets, and then we compute the value of this valuation by doing the unions and the intersections. So the value of the whole thing should be, if I break it into these 4 pieces, I should add together those 4 values and then subtract away the intersections, which are these lines, right? What is this? Well, we can compute these ones, the little ones, right? Actually, all of these things down here are convex sets now. These regions, these sort of trapezoidal shapes, and then these lines are also, they're all convex, so the chi should equal 1 for all of them. So the value here is that, right? 0. I know my students are always disappointed when I do sort of a complicated thing and end up getting 0. They feel like I've wasted their time. I hope you don't feel that way. This is equal to 0 on this set, though, all right? If you want something that's not 0, it would have to be even more complicated than what I just did, so you should thank me that I did this example. All right. Actually, you can do this computation in a more systematic way. If you have some kind of a shape like this, you can do what's called a triangulation. You've probably seen this before at some point in your life. And then when you want to break up the value in terms of the convex sets, which are all of those little triangles, what you're going to do is you're going to add together the valuation on the triangular faces, and then you have to subtract away the intersections. If you think about this, I'm going to be a little fast and loose here, but the intersections, you know, all the faces, you're going to add them all together, and then you're going to subtract the intersections, which are the line segments. It turns out actually the line segments intersect each other, though, on the vertices, and if you work this out, you can see that when you do this valuation, so you decompose the space as faces, edges, and vertices, and then what you do when you add up, so you add up the value on all the faces, but the value is always equal to 1 on the faces. So really what you're adding is just the number of the faces. You're adding 1 plus 1 plus 1 for every face. And then you subtract the intersections, which are the edges. It turns out you're just going to subtract the number of edges, but then the edges are intersecting each other in the vertices, so you're going to have to add back in to compensate for the fact that you subtracted too much when you subtracted the edges. You add in the vertices. Yeah.
What about the edges on the edge?
Yeah, I was hoping nobody would ask me, what about the edges on the boundary? Like this edge up here is not actually being double counted. It's not part of the intersection of any 2 faces, and it's true. My answer to that, I thought, what if someone asked me this question? Here's what I'm going to say. It turns out this formula here still is going to work out. You have to think a little bit more. So because this one is not part of the intersection, it turns out that's going to make some other change in the number of vertices or in the number of faces, which will compensate for the degree to which this formula is messed up. It'll affect the other things in a nice way. So if you either don't think about what he just said, or believe me when I say this is going to work out anyway, it turns out this is the value that you will always get if you do a triangulation. Does that look familiar to anybody? There's a name for this actually. Yeah, this is called the Euler characteristic. The Euler characteristic. It's something that people have been doing for a long time, since Euler. Sometimes it's called the Euler-Poincaré characteristic. All right. So, and that is a continuous invariant valuation. So the continuous invariant valuations in Rn include the intrinsic volumes, also the Euler characteristic, and actually because of this sort of list which I'm writing right now, the Euler characteristic, when you're doing this kind of thing, is referred to as the intrinsic volume of dimension 0. And any linear combination of these, because it's a vector space. Any more? The answer now is no. That's it. These are the only continuous invariant valuations. And that's Hadwiger's theorem. So from 1957. The intrinsic volumes in dimensions 0 through n, so 0 is the Euler characteristic, the other ones are perimeter, area, volume, etc., are a basis for the vector space of continuous invariant valuations. Right? This is Hadwiger's theorem. Pretty awesome, right? I don't know if you think this is awesome. I think it's pretty awesome. What that means is any possible measure of bigness is some unique combination of the intrinsic volumes and the Euler characteristic. And there are no others. If you think you are thinking somewhere deep down inside your heart, if you're thinking of another valuation, you say, I think you missed one. I say, I didn't. Whatever you're thinking of, it must actually secretly be a linear combination of the intrinsic volumes and the Euler characteristic. It's an interesting fact. In R3 specifically, that means any measure of bigness, if you're thinking of some measure of bigness, it must actually be a sum of the Euler characteristic, the perimeter, the surface area, and the volume, all right, with constants in front of them. It's a neat fact, I think. This is something, when I heard about this, I heard about Hadwiger's theorem for the first time sometime less than a year ago, fairly recently. I thought I really should have heard about that before, but I hadn't. Now you all have. Since then, I've been doing sort of informal polling of mathematicians who I see. Have you heard of Hadwiger's theorem? Total number of respondents who said yes is 0. So I don't know these people. I guess there must be a lot of people who know about it, but I think this is actually kind of a beautiful theorem because the valuation property seems fairly general. That is to say, when I think about the valuation property, I feel like there should be a lot of weird functions which satisfy it. Turns out, though, there isn't. Many functions ought to obey this, but actually only the intrinsic volumes and the Euler characteristic obey this. The classification, in my opinion, is much simpler than it should be. This is part of what is ascribed to mathematical beauty. When things turn out to be simpler than you think they ought to be. It's also beautiful when things turn out to be more complicated than you think they ought to be. Actually, so I do topology. I don't do much geometry, so I don't usually talk about or think about volumes and areas. But topologically, this is also very interesting because the Euler characteristic of those continuous invariant valuations, the Euler characteristic is the only one which is purely topological. That is, it doesn't depend on the geometry at all. It doesn't depend on distances or how big or small things are in the traditional sense of geometry. So the Euler characteristic is the unique topologically invariant valuation, and that's a very interesting fact from topology. All right, a lot of topology is about coming up with invariants that measure spaces based on their topological structure, right? And the valuation property, I think, is a pretty natural thing that you would want your topological measurements to obey the valuation property. From the point of view of topology, it's a very natural thing that you want. And there are similar kinds of things for, say, I don't know how much topology you know, but you may have heard of fundamental groups. There's something called Van Kampen's theorem, which tells you how to find the fundamental group of an intersection related to the fundamental groups of the unions and the each things. And there's a similar thing in the homology groups, the Meyer-Viator sequence. So the kind of idea of how does the topology of the whole space relate to the topology of subsets and their intersections, that's a very common idea in algebraic topology. So it turns out if you want an algebraic topology invariant, which is going to be real number valued, it has to be the Euler characteristic. That's the only one, if you want it to satisfy this kind of subsets and intersections property. All right? Must be a constant times the Euler characteristic. So, the Euler characteristic is always an integer. So it says actually the only real valued invariants are actually the Euler characteristic, which is an integer. So there aren't any real non-integer topological invariants which have this valuation property. Interesting fact, I think. So here's what remains in my talk. I got about 20 minutes left, I think. Why the theorem is true, I'm not going to get into real technical proof, but actually it's not too hard to see. I'm going to draw a lot of pictures. and some real-world applications. I really mean it. I don't mean like applications to, you know, algebraic geometry or something like that. I mean real, really real world applications. This isn't going to change your life in the next few hours, but okay, why it's true. First of all, let's try. I want to give an idea of why any continuous invariant valuation must be one of the intrinsic volumes or their characteristic. Just a little heads up. There's some familiar big ideas coming. Get ready. Start your anticipation. The intrinsic volumes. So as we know, there's sort of one for each dimension. All right. So I'm just going to focus on. Let's just talk about the dimension 2 valuation. I want to show the only dimension 2 valuation in R2 is the area. Actually, this is a little too vague. More specifically, we're going to show the only continuous invariant valuation, which is 0 on sets of dimension less than 2, is constant times the area. This is what I'm actually going to talk about. All right. So by dimension 2 valuation, I mean a valuation which always gives you 0 unless the thing is a set which somehow has dimension 2. And I'm not actually going to talk about what that means. That's actually kind of a complicated idea. Anyway, this is what we're going to talk about. All right. So let's start with any continuous invariant valuation on R2, which is 0 on sets of dimension less than 2. All right. My goal is to show that V is equal to the area, or actually a constant times the area. Right. Here we go. Here's the pictures are going to start now. Okay. So we're going to show V is a constant times the area. Right. That's our goal. First, let's consider the unit square. It has some value. Let's say C. All right. Actually, that's the same as this C. It turns out that really will be the same as this C right here. Could be 0. That's fine. The unit square has to have some value in my mystery valuation. My goal is to show that this valuation is a constant times the area. All right. So by the invariance, that means actually any square of area 1 will have the same value, right? Not just like the unit square next to the origin, right? But any square of area 1, any 1 by 1 square, yeah. That's the same as square of area 1, right? We'll have the value C, okay? What about other shapes? So this one, if you start with the unit square, you can do the valuation property, right? You break down the square is the union of the left side plus the right side, and then the intersection is the line in the middle, all right? So, and this thing I said I'm going to assume that it equals C, some number, all right? You can use the valuation property to do this. Let's do some more stuff here with this, all right? What can you do here? Well, first of all, the line over here is not a dimension 2 set, and I assume that my valuation was sort of a dimension 2 valuation. So this one over here is 0, right? That's what I assumed. So it's actually this. What can you do with those two sets? Well, actually, the second one is the same as the first one by a rigid motion. So this one right here, the value must be the same as this one. Those are the same, though, so we can add them together. So it's 2 times the value of the first one. And if you just move things around, you'll see the value of that half square is 1/2 C, right? So V on the unit square has value C, right? C times 1. V on the half square has value C times a half. Isn't that nice? See where I'm going with this? Remember, my goal is to show that V is C times the area, right? Doing pretty good so far. It works for the unit square, and it also works for the half square. All right. What about other shapes? Well, by cutting it up in different ways, it's actually, you don't have to just do the half square. You could do like a third of a square, and by doing the valuation thing again, it's the same idea works to show that that would have C times 1/3. All right. In fact, any rational number, you can show that the value on a rectangle with area Q, a rational number, is always C times Q. If you want, what's the value on the rectangle with area 82 over 705? Then you cut it up into 705 pieces. Each one of those has value 1 over 705, and then you add together 82 of them, and that's 82 over 705. Anyway, all right. So already it's starting to look like V is just C times the area, but I've only said this for rectangles. So what about non-rectangles? Some shapes are not rectangles, right? How about this? Could you possibly find the area of that set, even if all you knew how to do was the area of rectangles? I think you could, right? What if our shape isn't a rectangle? Well, you can still break it up into rectangles. That one, at least. You can break it down into rectangles, and you can compute the value. And it'll still be true if you break this into a bunch of rectangles. Then the value on those rectangles has to be c times the area. And so if you add them all together properly, the value on this whole weird shape will still be c times the actual area of this shape. All right? Just because it works for rectangles and you add them all up, it'll still work for that weird shape. What if it's even weirder than that? What if it's a curvy shape? Say the area under the curve of a parabola. You should start to feel a little reminiscence from your youth coming on here. Can anyone imagine, how could you find the area under the curve of a parabola if all you knew how to measure were rectangles? Is there a way to do such a thing? I think you all know what I'm talking about here. Cover it with rectangles. Cover it with rectangles. I put it in all caps because it's such a classic idea, right? That shape, the area under the curve of the parabola, is sort of infinitely close to this, what I call this sort of rectified region of the area under the curve, all right? It's close to the area of the curved region. And, as we all know, as the rectangular approximations get sort of smaller and closer, the area of the rectangle thing will approach the actual area of the curved shape, all right? So the area of the rectified version will approach the actual area under the curve. How do you know that this also is true of our mystery valuation V, right? Remember, V is equal to the area for rectangles, but we don't know if it's equal to the area for other kinds of things. There's actually one property of our valuations which I haven't mentioned yet. We use the subsets and the intersections thing all the time. We also use the invariance. What's the other thing? Continuity, all right? It's because of the continuity property. We already know V is C times the area for the rectified areas. Will it also be true for the curvy area? And the answer is yes, because V is continuous on convex sets. And as you make those rectangles approach the actual curvy area, because V is assumed to be continuous, it means the value of V will also approach the value of V on the curvy area. All right? So here's the whole idea at once. If you say V has some value C on the unit square, the value on the square tells you exactly what the value has to be on any rectangle. And because of the continuity, this tells you exactly what the value has to be on any curved area. So in other words, any dimension 2 measurement which you can break down like this must actually be the area times the constant C. Right? And that's it. That's the whole idea. So this is sort of like a dimension 2 Hadwiger theorem. The full Hadwiger theorem is quite a bit more complicated because you have to do this in any dimension. And then you also have to do this kind of like in dimension 0 for the Euler characteristic, which is doesn't resemble this argument at all. But it's that's the basic idea, though. This is why you should feel like it's true, anyway. Any questions about that? All right. Okay, real-world applications. So Hadwiger's theorem says any continuous invariant valuation is a combination of the intrinsic volumes. All right. Most things in nature, in the real world, are continuous and invariant. That is, I'm not talking about quantum mechanics, which is not continuous, and I don't know about invariance, but maybe nobody knows. Anyway, let's just talk about big things in nature. So if you encounter in nature a valuation, it must be a combination of the intrinsic volumes, including the Euler characteristic. All right. I'll just say, because I'm about to talk about some things, some science, what I'm about to say is mostly true. I read some papers and I didn't completely understand everything, so I'm going to try and give you the basic ideas. Mostly true. Also, like most things in science, you know, things tend to be, you tend to make up formulas which hold sort of to like a first degree approximation. So some of the things that I'm about to tell you are only approximately true, but that's good enough for me because I'm not a scientist. All right, so this is a great paper. If you're interested in this, you can check it out. Additivity, Convexity, and Beyond, Applications of Minkowski Functionals in Statistical Physics. Minkowski Functionals is another word for intrinsic volumes. So this is a physicist who wrote this paper. 74 pages of examples where the intrinsic volumes in Hadwiger's theorem have been applied in the real sciences. So I'm just going to describe one of them, which is called the curvature energy of a membrane. And this is probably very closely related to what you guys were talking about a few minutes ago. If you have a flat, flexible membrane, which either you just ideally assume has no thickness or a uniform thickness, how much energy is required to bend a flexible membrane? That's called the curvature energy of the membrane. All right? depends on what the thing is made of, other physical properties. We're going to just assume that all of that is constant. So it has a uniform composition, chemical, whatever it's made of. The temperature is constant. Everything is constant. The only thing that I'm going to talk about is the shape of it, all right? Curvature energy depends on the shape. Well, what could it depend on in terms of the shape? Obviously, it might depend on the total area. If the thing is really big, it might be harder to bend it. Really small might be easier. I don't know. How exactly does it depend on the area? Probably something like this, right? Actually, I just, at random, wrote some complicated formula. The energy is proportional to that function of the area. Actually, when I say how exactly does the curvature energy depend on the area, the answer is I don't know. I mean, I'm not a physicist, right? You'd have to do some work to figure this out, right? And there's nothing, no obvious answer that you should just say, oh, obviously the energy is proportional to the area or the area squared or whatever. I don't know what it is. It probably depends on the area. Anyway, beyond just the area, it probably depends somehow on the shape, like specifically in this case. I had to do some work to make this picture. It doesn't look too impressive, I know. These are two shapes of the same area. Are you impressed yet? Think about how you would do that. It's not too hard. Is the curvature energy the same for these two things if they're made of the same thing? All right. They have the same area, but they have different shapes. And so it seems, I mean, if you don't already know something about this, you say, I don't know, maybe. I guess they probably do. I don't know. They have the same area, but they're different shapes, right? How about this? You should be more impressed with this one. These two shapes have the same area and the same perimeter. Just think about that. It took me several minutes to figure out how to draw this picture. How about these? See, this rectangle is a little smaller than that one because I took out that area. It also has a slightly bigger perimeter. You impressed yet? Anyway,
Question.
yeah.
Did you do it with like string and stuff?
No.
No.
I have I don't know if you can do this in Photoshop. There's something called GIMP, which is an open source version of Photoshop, and you can actually measure the area of things. And then, so I measured the area of that. I also measured the perimeter in my graphics program. And then I made a box which has the same area and the same perimeter. Turns out actually there's a unique rectangle which has a given area and perimeter. Anyway, a little something to think about. Anyway, so the two shapes on the top have the same area and the perimeter. Does that mean they're going to have the same curvature energy? I mean, they have totally different shapes, right? And the same is true for the ones down there. Okay, we expect the curvature energy to depend on the shape and probably in a very complicated way. I guess the best imaginable situation would be like a simple mathematical formula for the curvature energy in terms of something or other based on the shape, all right? And it turns out, maybe you can see where I'm going with this. This seems probably impossible. I know it's not impossible, though. That's why I'm talking about it. Turns out the curvature energy is a valuation when you do it in this specific physical setting. It turns out the curvature energy does actually satisfy the valuation property. It's also continuous and invariant. All right? And so, because of Hadwiger's theorem, it means it must be a combination, a linear combination of the Euler characteristic, perimeter, and the area. All right? That's what Hadwiger's theorem says. So, if you're a physicist, this is like a miracle, right? You don't have to do anything. You don't have to do any kind of experiments. You already have a formula for the curvature energy, like for free, all right? It depends only on the Euler characteristic, the perimeter, and the area. I guess you have to figure out what the constants are in this formula. But otherwise, you get the whole thing for free, right? It's pretty nice. The formula is obtained purely mathematically, no experiments necessary, other than the experiments that it takes to figure out that it's actually a valuation. You'll have to do some work to do that. All right? The only things you need experiments for are to figure out what the constants are. And actually, even if this is all you know, even if you don't know the constants, you can answer conclusively each of the questions that I asked. So the curvature energy depends only on the area, perimeter, and Euler characteristic. So what about this one? Is the curvature energy the same for these? The answer is no. They have the same area, but they have a different perimeter. All right? Unless that constant is 0, right? And so in these answers, I'm gonna assume that those constants are not 0. Certainly, they're not all 0. And so in the real world, those constants are not 0. None of them is 0. So the answer here is no, because they have different perimeters. Even if you don't know anything, it's just because of the valuation property. How about these ones? Is the curvature energy the same? The answer is yes. Remember, I made sort of a big deal about the fact that these have the same area and the same perimeter, right? So that means, and they do have the same Euler characteristic also, because topologically they're the same. So the answer is yes. They have the same area, same perimeter, same Euler characteristic. How about these ones? The answer is no. They have the same area and perimeter, but they have different Euler characteristics. So as long as the constant in front of the Euler characteristic is not 0. Yeah?
Top one polyconvex. Which polyconvex?
No, it's not. Well, no. I think maybe it is. Polyconvex is a union of convex sets. I think I can make this with a union of, this blob, union this blob. I think it is. Maybe not. Maybe not right here. I'm not sure about that.
Right, well, it depends on
No, and annulus certainly would be, because you can do this. And these are each convex.
These aren't quite convex, because it's a circle on the inside.
Oh, here. Yeah. You're right. Yeah, that's actually why, I did know that. That's why my picture was this. And earlier in the talk, I drew the inside like that. But this may not be quite polyconvex, but it is arbitrarily approximable by polyconvex sets, and so by the continuity, that it doesn't really matter. As long as I'm not including like Cantor sets up here, any kind of reasonable shape that you can draw like this is either polyconvex or it's arbitrarily approximable by polyconvexes. Yeah. Thanks for asking. So the answer here is probably no, because they have different Euler characteristics, even though they have the same perimeter and the same area. All right. The top one has Euler characteristics 0. The bottom one has a 1. All right. So the moral of the story here is, if you ever encounter a valuation in nature, Hadwiger's theorem will give you a formula for whatever it is you're thinking of. You get a formula for free. All right. So I don't want to talk too much more about other examples here. So one other example in this paper that I talked about before is percolation threshold in porous solids. I really didn't understand much of anything about this section of the paper, which is why I'm not going to talk about it. But the idea is you have like a block of styrofoam or something with a porous thing, and you want to study, there's a certain threshold of porousness. If it's really, really porous, then water will be able to flow through it, and that's called percolation. And if it's not porous enough, then water will not be able to flow through it. And so there's something called the percolation threshold, which is like, how porous does it have to be for the water to flow through? It turns out, apparently, that sort of a thing, there's a way of thinking about that in terms of a continuous invariant valuation, and you get some formulas for free that you wouldn't have predicted otherwise. This is also related to stuff about hearing the shape of a drum. This was kind of a big question that various people studied starting in the 60s. The basic idea is, when you hear the sound of a drum, or any sound that you hear really, what you hear is sort of, if you think of it musically, there's like a bass tone, and then there's also a whole collection of what's called overtones, which go along with every sound that you hear. And so if you talk about like the pitch, this is why, say, a violin playing a certain note sounds different from a piano playing a certain note. They have the same bass pitch, but the series of overtones, which is a bunch of like nearby frequencies that go along with the bass pitch, the series of overtones are different. Anyway, the question that people started asking, like in the 60s, was if you just hear a single sound that's made by a drum, if you know it's made by hitting a membrane, if you can hear the whole spectrum of overtones, will this allow you to deduce exactly the shape of the drum that made that sound? All right. The answer is no, but it wasn't until the 90s that it was actually shown an example of two different shapes which have the same spectrum of overtones. It has to do with the eigenvalues of certain operators from physics. Anyway, hearing the shape of a drum. This also, though, is about valuations. If you look at it in a certain way, it turns out actually for two drums to have, so it is possible to have two different shaped drums give you the same sound, but those two drums must have the same perimeter, area, and Euler characteristic. That sound familiar? Yep. Interesting stuff. Actually, I was reading about this. So the question was first posed in the early 60s by someone named Katz. And immediately, John Milner, the famous topologist, responded and gave an example of two 16-dimensional manifolds which are geometrically different but have the same spectrum of overtones. It was not what they were looking for. It wasn't until the 90s that the problem was actually solved in dimension 2. That sounds, I don't know much about Milner, but that's the kind of thing that he would come up with, it seems. Sean knows more about it. Yeah. He's sort of famous for ridiculous, strange manifolds in high dimensions. I don't know if you care about this, but how I came across this Hadwiger's theorem. I'm interested in the Euler characteristic as a topologist. And there's another theorem from the 60s by Watts, which, if you look at it, Watts' theorem looks just like Hadwiger's theorem in dimension 0. So here's the Hadwiger theorem in dimension 0. The Euler characteristic is the unique function, which has the valuation property, and the Euler characteristic of a convex set is 1. That's how I sort of introduced the Euler characteristic before. That's the Hadwiger's theorem. Here's Watts' theorem. He says the reduced Euler characteristic, which is Euler characteristic minus 1, is the unique function with these two properties. I don't want to really get into this, but in Watts' theorem, the two properties, the first one is sort of an additivity property. You could write this as addition by moving it to the other side. And then the other one is saying the Euler characteristic of a certain thing is 1. All right? This S0 is actually the zero-dimensional sphere, which is just a union of 2 points. So when I saw Hadwiger's theorem, it reminded me immediately of Watts' theorem. But it's not the same. There's no obvious equivalence between the two results. So my research is in topological fixed point theory, and something that we talk about a lot is something called the Lefschetz number of a function from a space to itself. I'm not going to talk much about what it is, but it is a fact that the Lefschetz number of the identity map is always equal to the Euler characteristic of the space. So the Lefschetz number, if you think of it in this way, is a generalization of the Euler characteristic. So you could think of the Lefschetz number as like the Euler characteristic for a function, right? You have the Euler characteristic for a space. If you want to do a similar kind of a thing for a function, there is such a thing. It's called the Lefschetz number. And from 1962, we have Watts' theorem, which says the Euler characteristic is the unique function which satisfies this and that. We should try to prove the same thing for the Lefschetz number because the Lefschetz number is a more general version of the Euler characteristic. This is a classic sort of thing that mathematicians do. If you know a fact is true for some kind of a simple thing, you try to show the same thing is true for a slightly more complicated thing. All right? And this was done in 2004, Arkowitz and Brown. Brown was my dissertation advisor, so I knew about this paper when I was a grad student. They showed that the reduced Lefschetz number, that is the Lefschetz number minus 1, is the unique function which satisfies blah, blah, blah. And the properties which they gave were basically the same as in the Watts' theorem about the Euler characteristic. Okay? So you take Watts' theorem about the Euler characteristic, you try to sort of do the same thing, and you get a theorem about the Lefschetz number. All right? In the same year, actually, there was another proof of the uniqueness of the Lefschetz number, which used different properties. It said the Lefschetz number is the unique function that satisfies blah, 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 but those blah, blah, blah were different from the ones that Arkowitz and Brown used. So it's been kind of an active area lately for people to find properties which uniquely characterize the Lefschetz number. All right? And I did some stuff. I actually wrote 3 papers following up and extending the Fourier-Paris-Bedini stuff on the Lefschetz number. So I was pretty involved in this kind of a thing. So when I saw Hadwiger's theorem, it immediately occurred to me I could do something like what Arkowitz and Brown did with the Watts' theorem. They used Watts' theorem and did the same thing for the Euler characteristic. So I saw Hadwiger's theorem. I probably wouldn't have noticed it other than this. It looked like Watts' theorem, and I thought you could get a similar thing about the Lefschetz number. And so this is my new theorem, which I've just sent to a journal last week, I guess. Anyway, this isn't going to make any sense, but there's a unique function, lambda, which is the Lefschetz number. And I just want to bring your attention to this. This is the valuation property. This is something that says something or other is equal to plus or minus 1. This is a plus or minus 1, and this C, which is defined in my paper, is also equal to plus or minus 1. So what you get here is either 1 or negative 1. Remember, in the Hadwiger's theorem, this was always equal to 1, right? In the case of the Lefschetz number, it turns out it could be plus or minus 1. And then you needed another little continuity thing because of the F Hadwiger's theorem, there was no function. You didn't have to have any assumptions about the function. If you have a function, you have to have an extra thing. Anyway, I thought maybe that would be a little interesting. This is kind of what you do. Hadwiger's theorem is back in the 50s. Why hadn't somebody else thought of doing what I had just done? It's because I guess people in fixed point theory don't know about Hadwiger's theorem. I went to the international meeting of topological fixed point theorists was last month. And I gave a talk about this, and then I asked everybody there, have you ever heard of Hadwiger's theorem? And nobody said yes. So this is what is referred to as low-hanging fruit in the research mathematics. I think probably anybody else could have done this. It's just nobody who knows about the Lefschetz number also knew about Hadwiger's theorem, or vice versa. I'm happy to take credit for it, though. All right. Actually, a more interesting question is looking at the higher dimensions, right? If Euler characteristic is like the Lefschetz number, that suggests that the higher dimensional intrinsic volumes should be kind of like something else, some higher dimensional kind of a Lefschetz number. But there is no such thing that anybody knows about. There is no such thing as a higher dimensional kind of a Lefschetz number. So that's something that I'm looking at currently. That's all. Thanks.